We are back at binary search trees today looking at searching and insertion. At the last video, we ended with this idea of binary search trees, where if we have this tree, and it's certainly a binary tree, but what makes it a binary search tree was this ordering property, where if we look at this tree up here in the upper right of the screen, you should be able to see some type of organization of the nodes. And in fact, what we see is for each node n, all of the values stored in a left subtree of n are going to be less than the value stored at node n. And also, then this is true for every node, for all of the values, for each node n, all of the values stored in the right subtree of n will be greater than the value of n. So pick this node 8, all of the nodes to the right of 8 are larger, all of the nodes in this left subtree are smaller, and that rule holds, that ordering property holds for every single node. Pick this node 6, everything to the left is smaller of 6, everything in the right subtree of 6, which is now this 7 here, will be larger than 6. Why is this property advantageous? We mentioned because now searching becomes super fast. Normally, a search would take O of n over a linked data structure, a dynamically linked data structure, such as a linked list, right? We no longer have direct access, so we can't take advantage of binary search when we had a sorted array. Even if you have a sorted linked list, it's going to be O of n for that search. Well, now we have this dynamic data structure, and we've effectively embedded the idea of a binary search into this data structure, which is super, super big brain and cool. So now searching is going to be super fast because instead of searching through all n of those nodes, we can really start here at the root. Imagine we're looking for node 13. Hey, 8, are you 13? No. Where's 13? Is it smaller? No, it's not smaller. Okay, it must therefore be on the right side if it's in the tree. So we go to the 10. 10, are you 13? No. Where's 13? Is it going to be, smaller? Is it smaller than you? No, it's not smaller. Okay, it must be therefore on the right side because it's bigger. Let's come here. 14. Are you 13? No, I'm not 13. Is 13 smaller than you? Yes, it is. So we come to the left of 14. Hey, are you 13? Yes, I'm 13. And see, so instead of now searching through all 9 of those nodes, we only had to search through 4 of them. Searching becomes super fast. It would normally be O of n, but because this ordering property tells us to either go left or go to the right, we're effectively dividing the search space in half at every single iteration of this search, which really smells like and feels like log n. And I want learners to always remember, when you think of binary search trees, and I say searching or insertion, running times, I want you in your heart of hearts to think log n. I want you to remember log n, but it's not O of log n. Big O means worst case scenario. Pause the video and try to think about why would it not be worst case scenario log O of log n for this traversal. In fact, I'm going to tell you it's O of n to search this tree, not O of log n. I'm going to tell you it's O of actually n, where worst case scenario, you have to look over in nodes. Pause the video, but now here's the answer. If I come over to the tablet, if you look here, what we have is I have 8 nodes. That is a tree, even though they're all on a line, but that is a tree. It's a binary search tree. All nodes to the left of a given node are smaller. Well, there is nothing to the left. That's how I've designed it. And then all of the nodes that are larger are clearly going to the right of a given node. So 2 is the root, 3 is to the right of 2, 6 is to the right of 3, 8 is to the right of 6, all the way down to 15. This is a binary search tree. In fact, it is. But it's really, you could say, a linked list in binary search tree clothing because of the way the insertions occurred on this particular tree. And we're going to cover insertions in just a bit. But because of the order that the insertions occurred in, the consequence is that these nodes all come to the right of each other. And now, if we're looking for node number 15, well, we effectively have to search over all 8 of those nodes. We would start at the top. We'd say, hey, are you 15? No. Is 15 smaller? No, it's not. So we come here. Are you 15? No. Is 15 smaller? No. So it must be bigger. Come here. Are you 15? No. Is it smaller than you? No. So therefore we go to the right. And we keep going right, 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 right. And we finally find 15 right here. And we had to loop over all 8 of those nodes. So in fact, worst case scenario, big O running time, searching within a binary search tree is actually O of n. Well, then why do I want you to remember this idea of log n in your heart of hearts? Well, because the spirit of binary search trees is that you're not going to have what we just depicted here. That's a rare, very extreme, worst case scenario example. But in general, you're going to have some nodes on the left, some nodes on the right, but you have no guarantee of that balanced tree with strictly a binary search tree ordering property. But here's the but. If we had a guarantee that our binary search tree was complete, that term that we mentioned last time where every level is filled 100% with only one exception, the last level does not have to be filled. So if we now have this complete binary search tree, therefore it's fully balanced, now we can guarantee that it will be O of log n for that searching on a binary search tree. So I want you to remember O of log n. I want you to remember log n in your heart of heart, because that's really what we're going for. That's the advantage that binary search trees bring us. But in fact, if we're talking big O, and we have to be a stickler on that, worst case scenario, searching in a binary search tree is still going to be O of n, simply because we care about worst case scenario. What if we have a hideous tree that ended up looking like this, and it's not really taking advantage of this value of the ordering property of binary search trees? While an extreme example, that can happen. That's the worst case scenario. So searching would be O of n, but I want you in your heart of hearts to remember log n, because if that tree could be balanced, meaning equal number of nodes basically on the left and the right, close to equal enough, we would then get O of log n. So now let's show you how we go search for this node. We just get an example of 13. Let's look for 7. Hey, 8, are you 7? No. Is 7 smaller? Yes, it is smaller. So we go to the left. And now we say, okay, we're at this node 3. Are you 7? No, I'm not. Is 7 smaller? No. Okay, so we go to the right. And now we're at 6. Are you 7? No, I'm not. Is 7 smaller? No, it's not smaller. So we go to the right. And here we are at node 7. Are you 7? Yes, I'm 7. Nice to meet you. And they get really excited. We find the node and we return true. That's the process. Let's take a look at the code. I'm going to show you 2 examples of the code. One iterative, one recursive. Neither's better than the other. You might have a preference. I have a preference, but let's look at both of them. I say here at the bottom, I don't like this one. The better one's coming. They're both good. Here is the iterative version of searching for a node. And it's basically what we just did. Because imagine if we were looking for, how about we're looking for the number 2. Start at the top. Are you 2? No, I'm not. Is 2 smaller? Yes, 2 is smaller, so I come to the 3. Are you 2? No. Is 2 smaller than the 3? Yes, it is, so we come to the 1. Are you 2? No, it's not. Is 2 smaller than you? No, it's not smaller, so therefore, if 2 is in the tree, it must be to the right of the 1. And when we come to the right of the 1, we're right here, and it's empty. And so we've reached this null, right? There's no more nodes there, and that's how we actually exit. So I gave that example to now show you, look at the condition of this while loop. While p is not equal to null. And what is p? P, right at the beginning, points to, it stores the address of our root, and we're looking for this key value. Let's say we're looking for that 7 again. While p does not equal to null, so while we're actually looking at a node, if 7, the value we're looking for, is equal to the value that's stored in that node that p is pointing to, return the address of p. Or we could have said return true or false, but it's better to return the address. But now, else, if 7 is less than this 8, the data that p is pointing to, what do? We say p equals p left. We should be okay with that. That's like help pointer equals help pointer dot next. P equals p left. It says take the address that is in p left. So if p is pointing to 8 and p left is pointing to 3, it says take that address of the node 3 and save it into p. So now p is going to point to node 3. And we continue the while loop. While P is not null, 3 is not null. If the data value 7 that we're looking for is equal to this node, it's not. So now we say else if the data value 7 is less than this node, it's not. So now we're at the else, and we say P equals P right. And so now P is going to point to this node 6. And we're still in the while loop. While P is not equal to null, we keep on trucking. If 7 is equal to this node, it's not. Else if 7 is less than the data value of this node, it's not. Else we have P equal P right. And so now P is going to point to this node 7 here. And finally, we say while P is not null, it's not null. So we're still pointing at a valid node. If 7 equal P dot data, it does, we could return true or false, or we could actually just return what we do here, the address of the node. There's your iterative search. And if we never find anything, and we end up at a null value where P is null, we then exit the while loop and we return null, indicating that we actually never found a node. Here, I say better solution. I like recursion, but here is another solution where it's going to be recursive. If the tree is null, return false. Else, check the root node, the root being the root of whatever subtree you're at. If the value we're searching for is in the root, we could return 1, or we could return its address as we just saw. But if it's not in the root, if the value we're looking for is less than the root, we're going to recursively call the left subtree. Otherwise, we recursively call the right subtree. So here is the recursive solution. And we have, as we've seen previously, we have a public version of our method, and then we have a private version of our method. The public version is really just calling the real recursive search, the private version. And so this recursive search public version, we're saying we're looking for this data, and then we're going to call the real recursive search looking for this data at our root of our tree, which was a private data member. So this is all about information hiding, maybe overkill, but here we have these two methods. But let's look at the real recursive search method. So we're looking for this data starting at node P, which is our root. We sent over the address of the root, it got saved into node P. We say right off the bat, if P is null, meaning at the beginning, if there wasn't even a tree, then we need to just return false. We never found it. But now, if the data we're looking for is equal to P data, return true. Else, if the data value that we're looking for is less than P data, here's what we do. We're going to look to the left recursively. So we're going to return a true or false because it's a Boolean method, right? The contract of the method header says you must return true or false. So we're going to return, but what are we going to return here? We're going to return the recursive call to the left. And ultimately, that recursive call, it's going to return true or false, which will end up coming right here. But we're going to return recursive call, and we call it to the left with our data value. And that was strictly if the data was less than P data. Else, we return a recursive call to the right, looking on the right side of that tree. So we've now seen those two search methods, both equivalent, one not better than the other. And we see that speed, that ordering property of binary search trees. Smaller look to the left, larger look to the right. Now let's talk about how we actually create our binary search trees. We want to insert nodes into our binary search tree, which means we actually need to create those nodes that we want to insert. We want to save the data value into that node, maybe set up a left and a right pointer, we'll get to that, and then insert that node into our tree. Here's the class that we showed you previously. We have this public class into BST node. It's just a teaching example. We have only one meaningful data member called data, right? Whoa, shocker. And then we have this left and right, which is of data type int BST node. Those will store the references, the addresses of the left and right nodes of this particular node. And here's the class with constructors, int BST node. Here we have a constructor where we just set the left and the right equal to null when we create that node. And then we have two other constructors if you wanted to create a node with already created addresses for the left and the right pointer. We need to make a class for our tree, similar to linked list. You have the LL node, which is the class of the nodes, and then you have the linked list class, which is going to be the class that maintains the list, that maintains that head, that maintains all of the methods, insert, search, delete, print, and what have you. So we need to make a class for the entire tree. This class is going to be called int BST, standing for integer binary search tree. This class will have one variable, super important variable, kind of like head is important for linked list. Well, here we will have one variable called root that will always store our access to the root of the tree. And then from our main method, now that we have this class created, we could create an object of type int BST. That'll be our object of this class, and we now have a binary search tree with no nodes in it, because when we make it initially in the constructor of creating that tree, we're going to set root equal to null, which should make sense. When we make a linked list, we said head equal to null in the constructor of creating that linked list. But now we have access to this empty tree, and we can call insertion methods on it, deletion methods, count methods, print methods, and what have you. So here's our int BST class. We have the one variable root. Of course, it is of type int BST node. Here is our constructor. We say root equal null, and then we have other methods here. Of course, the isEmpty method. We should be experts there. How do you know if a tree is empty? You would just say return root equal null. This should actually be public boolean is empty, and you just say return root equal null. Just like you say return head equal null. It evaluates that boolean expression and returns true or false, determining if the linked list is empty, in the same way determining if our tree is empty. So now that we have this tree, it's empty, but we've created an object of type int BST. We're ready to now insert nodes. What do we actually do? We have to maintain this ordering property, which means whenever we're inserting a new node, it either needs to go to the left of the previous node, or it needs to go to the right of the node based off of that rule. Smaller to the left, and then greater or larger items go to the right. And we have to strictly follow this rule. We're going to start at the root, and we either go right if it's larger, or we go left if it is smaller, and we keep doing this until when? Until we arrive at an empty position. And an example will make this super clear. So we have these data values we want to insert into a binary search tree that is initially empty. We want to insert 10, then 14, then 6, 2, 5, 15, and then 17. Step 1, the tree is empty. 10 is going to become the root, period, done. So now we want to insert the 14 next. Where's that 14 going to go? What did we just say? If it is smaller, it goes to the left, but if it's larger, it goes to the right. And we keep doing that process until we arrive at an empty position. So what happens for the 14, create a new node with 14, and it's going to ultimately come to the right of this 10, because that's exactly where it goes. We insert to the right. The right subtree of the 10 is empty, and that's where the 14 will go. What about now? This 6, I'm going to back up to here. I want to insert the 6. Where does it go? Well, we start at the 10. There's a node there. Does 6 go left or right? 6 goes left. When we come to the left here, it's empty. So the 6 will go right there. Now we're at the 2. Where does the 2 go? Well, start at the 10. 2 is smaller. Come to the 6. The 2 is smaller. Come to the left. And the 2 will come right here at the empty position. And that's exactly where the 2 goes. Feel free to pause the video, read along with this text. I'm not going to read the text. Hopefully it'll be clear as we go along on this silly or small example. So now we want to insert a 5. Where does the 5 go? Start at the 10. 5 is smaller. It goes to the left. Come to the 6. 5 is smaller. It goes to the left. Come to the 2. 5 is larger than the 2, so it goes to the right. We have finally arrived at an empty position with no node. The 5 comes right here where we just depicted. And now we're trying to insert 15. We start at the root. Where does the 15 go, left or right? It's bigger, it goes to the right. Come to the 14. We ask where should the 15 go, left or right? It goes to the right. And we're at an empty position, and we insert the 15 right here. Last one, 17. Where does the 17 go? We see it clearly goes to the right of the 15. So the example makes that really clear. Ultimately, you insert left or right based off of that ordering property, and you stop traversing down, going left or right once you get to that empty position. Now it's time to see the code. Our plan, and we want to do this recursively, is simply as follows. If the tree is empty, just return a pointer to the node that contains that new value right off the beginning. Say, hey, if P is empty, if P is null, return, and we make that new node and we return the address of that new node. Otherwise, check which subtree this new node should get inserted into. We compare the data values, right? We compare the data values and we either insert to the left recursively or we insert into the right subtree recursively. Here is our code to actually make this happen. Once again, we have that public method and we have the private method. We want to insert this data value into the tree rooted at this variable root, which is a private data member. So we call the real insert method here, and we send over the address of the root, and we send over the data that we want to insert. And we say right off the bat, if P is null, if there is no tree, make a new node with that data value and save it into P. And you're going to see down here, we're going to return P. Else, P is not null. We have a tree. We need to determine, do we insert on the left side or do we insert on the right side? So if our data value that we're trying to insert, if it's smaller than P data, we need to insert on the left. Otherwise, if it's not smaller, we need to insert on the right. And then regardless of that, we need to then return P at the very end. So this might kind of make sense, but it's going to be clearer if we can draw out an example. So let's go over to the tab and actually draw through some examples. I have the code here. It says nodes to insert, and we want to start by inserting 53 into an initially empty binary search tree, which means I'm going to save up here my root, and here is the address of the root, and it currently points over to null. So now we want to insert 53, and 53 is going to come to right here as the data value, and we want to insert that node. So immediately we're going to say if P equals null, and remember we call this real insert method by sending over the address of the root, and that address of root gets saved right here into P. So now when we say if P is null, what we're really saying is that initial root equal to null. It is null. So what we're going to do is we're going to execute this line of code. We're going to make a new node with the data value of 53. And we're going to save that into this variable P. So P points to 53. And then, of course, we do not do the else because we just did the if. And the last step is we return the address that is in P, which is the address of that node 53. That address then gets returned back to that public insert method, which really just said root equals, and it called this insert method. The consequence of all that is what? Is that when we return right here P and we return the address of 53, the consequence is now root is no longer going to point to null. Root is going to point directly to this new node 53, and that new node becomes the root. Great. Let's now insert this next node, 12. So when we insert 12, again, 12 is going to be the data value. When we call this method, and initially P is going to be pointing to 53. And so now let me erase this here. We're going to do this if statement. If P is null, well, P is no longer null because P is pointing to 53 right here. P in this moment is pointing to 53 again. And so it's not null. So now we do this else. And we say else. If the data value we want to insert, which is 12, if it's less than P data, it is, what do? It says we're going to call the insert method recursively. We're going to call it recursively. And we're going to send to this recursive method. So imagine we're going to come up to a new method call on the method stack. And we're going to send to this method two parameters. So here we're calling the insert method. And we're sending two parameters. What are the two parameters? We're going to send over P left. Well, what is P left? Here's P left. Here's P right. Well, P left is currently null. And P right is null. So we're going to send over null because P left is null. And we're going to send over the data value we want to insert, which is 12. So now we're calling a new insert method. Okay? And when we call that new insert method, we're going to come to a new version of this entire method because it's recursive, right? And when we do so, we're going to now try to insert 12, this data value 12 right here. We're trying to insert it into P, but what is P now? P is this null value. So now we're going to say if P is null, make a new node with that data value 12. So we're going to make a new node with the data value 12. And we're now going to return the address of that new node. So we're going to return the address of the 12. And that address of the 12, where does it get returned to? Well, let's remember this entire method right here, I'm circling all of it, that we called insert null 12. Well, where did we call that method from? It's from this line of code right here. This insert null 12 was referring to this part right here. So we called that line of code the right side of that assignment, this assignment right here. We called this line of code, and the right side of this assignment was this call right here, insert null 12. The consequence is we made a new node 12, and now we're returning the address of 12. And when we return that address of 12, where does it get saved? Well, we take all of this, and we're going to save it into p.left. That's what happens. We take all of that, and we save it into p.left. So let me erase all of this method that we called. And now the original p.left no longer points to null. Instead, it points over here directly to this new node 12. Check it out. That's pretty cool. Let's insert another one. Let's now insert this 74. We want to insert 74 now. And when we insert 74, we're going to come to this data value here is going to be 74. P, once again, is 53. And so now we're going to check, is P equal to null? P is not equal to null. So we come to this else statement, and we say, is the node we're inserting 74, is it less than P, which is pointing to 53? It's not less than P. Therefore, we come to the else, and we say, cool, let's insert it to the right. So we're going to execute this entire statement right here. But we start where? We start on the right side of that statement. And we're going to execute that right side, which is going to have us call this insert method. We're going to call the insert method. We're going to send over p.write. Well, you can see p.write, it points over here to null. So the first parameter is going to be null. The second parameter is going to be the data value we want to insert, 74. And here's that insert method that we're calling. Let me actually write it this way. That's the label. Here's the insert method. The consequence of this insert method is what? Since the parameter p is null, we're going to come to this if statement. If p is null, make a new node with the data value. So we're going to make a new node. And of course, I'm drawing it on the right side because that's ultimately we know we can see visually the 74 is going to go there because we're inserting where? On p right. So we make this new node and we return the address of that new node. So we're here, we're making a new node within this new method, and then we return the address of the 74. And when we return the address of that 74, where does it get saved? It gets saved into the original p-write of that calling method. So it gets saved right into this address right there. So now the original p-write no longer points to null. Instead, it points to this new node that we just created. And so now we have 3 nodes in our tree. And let's do one more. Let's insert this 74. It's going to get fun. Let me actually erase this here. I'm sorry, insert the 68. So now we're insert the 68. We start again at P, which points to 53. And we now need to, that's not null. So now we need to check, is 68 less than 53? It's not. So we have to insert to the right. So we're going to say p.write we're really setting this initial P dot right, and we want to say insert to the right of P, which means insert over here somewhere. And so we're going to call a new insert method. So we're going to have a new insert method that's going to get called. The left parameter, the first parameter is going to be saying insert into node 74. So I circle it to show it's a node, and we want to insert the value 68. So now when I come to this insert method, let's see what happens. P is now pointing to 74 within this insert method, this recursive insert method. Is P null? It's not null. So we're at the else. Is the data value we want to insert, which is 68, 68 is what we want to insert, is that less than 74? It is less than 74. Perfect. So now we're going to insert to the left of 74. So we're really going to insert this way to the left of this guy here. And we're going to call the insert method right here P left data. So we're really going to say P dot left equals insert, and now we're inserting. And what is P left right now? Well, if P within this method is pointing to 74, what's the left of 74? We can see it's null, and insert the value 68. So here we can see we have another recursive call. I hope we see what's going to happen when we call that recursively. Since the first parameter is null, ultimately we're going to get a new node that's created. That new node is going to be 68, right? Because if it's null, we have this situation. Make a new node, save it into this new value P within that method, and then return P. The consequence is of this entire, I'm going to highlight this again or underline it. The consequence of this recursive call is we now have a new node, 68. 68, of course, has a left and a right that both point to null. And we need to save. Remember, this is an assignment right here. This here is an assignment. We just did the right side, which said make this new node, call the insert method with null and 68, resulting in this new node. So we've just done that right side of the assignment. Save this new node into P left based off of the P of that particular recursive level, which was right here. P is currently pointing to 74. Save 68 into P left. The consequence of all of that, let me erase this. The consequent of all of that is now P, which at this level of the recursion was pointing to this node 74, and P dot left is right here. And so that is what we have. That's four trace throughs of inserting into this new tree of those four different values. We had here insert 53, 12, 74, and 68. So once we understand that, we can really see that we can now just in our main method, after making our tree, we simply call mybst.insert20, mybst.insert18. The 20 would have become the root. 18 is going to go to the left of the root. Then when we say insert 33, it'll go to the right of the root. And what we can see is what? That creating a BST, once we've made that object of type BST, it's then nothing more than a series of insertions, calling that insert method over and over and over. We're going to get method, maybe input from the user, maybe from a file, and we're going to then call this insert method again and again and again. And for each insertion, we're going to follow the rules of this ordering property, either inserting down to the left side or down to the right side until we arrive at an empty position, or you could say a new leaf position, and that's where we insert. Our interlude, human ingenuity, yeah, maybe, it's incredible. But another daily bike fail picture. These are my favorite. Sorry, I'm just weird. But when I was teaching at UCF, which is an incredible, my alma mater, incredible institution, but we saw too many of these bike fail pictures, and this was one of the worst ones ever. And so we started this. I got like dozens and dozens of emails from students with, when you have 300 people in your class, saying, hey, I found another one across campus. And some of these got really, really bad. So here is another bike fail picture. So what we like to now do is just solve a couple of practice problems with binary search trees. The first of which is counting nodes of a tree. How would you actually do this? Think of how you would have done it with linked list. How did you count the nodes? You would have simply traversed over the entirety of the list. You would have kept some counter variable, and each time you visit a new node, you would simply increment count. Pretty straightforward. Traverse the list, count the nodes. That's the same thing you could actually do here with a tree. And we've covered traversals. How do we traverse the tree? We've covered pre-order, in-order, post-order. You could simply do a traversal of that tree. You'd have to have like a global count since that method was recursive. That makes it kind of cheesy, therefore, to have this global count variable that you've initialized to 0. But then just do a traversal, and instead of maybe print left, right, instead of printing, you would simply increment the count, and then you would go left, and then subsequently you would go right. Pretty straightforward, but there's a better way. Pause the video. I would encourage you, spend, even if it's just 3 minutes, and think about how could you actually accomplish this? What could you do to actually go through and count all nodes of the tree? And the answer is, if there's no root, if there's no node at that root, right? How many nodes are there? 0. So return 0. Else, now, if we have a root, we have one node, so return 1, count that 1, and also count all of the nodes on the left plus all of the nodes on the right. And check out how beautiful this code is. If P is null, return 0. Else, return 1 plus. We count the nodes on the left, and then we count the nodes on the right. That is some sexy code. That is some absolutely gorgeous recursive code. Recursion, wonderful, wonderful, makes the problem solving so easy, and it comes up with beautifully succinct code. That's for counting the number of nodes. What if you wanted to sum the number of nodes? What would you do differently? What would you change? In fact, if you wanted to, instead of counting, sum the number of nodes, think about in this code what you would change. Pause the video. Give yourself 20 seconds, might be all you need. What would you change to sum up the values? So imagine we have just a tree of nodes where every node is just an integer value and then a left and a right. Instead of counting, what would you do to sum those values? And there's only one change that needs to be made. Here's the code. If P is null, return 0. There's nothing to sum. Else, instead of returning 1 plus, we return the data value plus we sum the left side, and then we sum the right side. Let's come over here to the tablet and very briefly take a look at this one and how would we actually trace through this code on this sample tree here that we have provided. So when we first call it, imagine we have this recursive call. I'm going to call the method sum node. So SN, and we're trying to sum node 4. And notice I put 4 in a circle within this parameter. Here I'm drawing the boxes, right? I put node 4 in a circle because I wanted to pick that parameter is an actual node value. So what does sum node 4 actually do? 4 is not null, so it's not going to return 0. What happens is it's going to return 4, which is the data value, plus some nodes, and we're going to send over the left of 4, which is node 2. I'm going to circle it, plus some nodes, and whatever is to the right of 4, which is node 6. And so now I need to call this particular method recursively. And we have here some nodes of 2. What does some nodes of 2 return? It's going to return 2 plus some nodes of null, because the left of 2 is null, plus some nodes of null, because the right of 2 is null. Now, both of these recursive calls here, when we call some node of null, let's open this up really quickly, some node of null, the parameter is null, what actually happens? Right here, we see the answer. It returns 0. So this will return 0, and then this right here, that 0 gets returned, and all of this becomes 0. All of this becomes 0. Let me erase what we have here. And so now some nodes of 2 ultimately results in 2 plus 0 plus 0, and then we return that value back to here, and all of this just became 2. And the same thing we then do for some nodes of 6. We come over here, and we now call some nodes of 6. What does it actually return? It returns 6 plus some node of node 5. So I'm going to circle the parameter, plus some node of null. And then we do this recursive call for some node of 5. And we have here some node of 5 as the parameter. And we have our final major recursive call, which is going to return 5 plus some node of null plus some nodes of null for the right side of 5. And so both of these end up becoming 0. That's 0. That's 0. So some nodes of 5 is 5 plus 0 plus 0, these 3 values here, which of course some nodes of 5 we can see is only 5. And so some nodes of 5 we return, it's a return statement, we return that total result, which is 5, to right here. And then of course some nodes of 6 here, of some nodes of null is 0. And we have, for the answer of some nodes of 6, we get return 6 plus 5 plus 0 is 11. All of this becomes 11. And finally, we have some nodes of 4 ultimately returns what? This value right here gets returned. 4 plus 2 is 6, plus 11 is 17, our final answer. Really cool to see how you then trace through all of those boxes. Let's look at 2 more problems. How do we search an arbitrary binary tree? Notice it's not a binary search tree anymore, just a regular binary tree that does not have the ordering property. So we have no guarantee that smaller nodes are on the left, larger nodes are on the right. So the searching will no longer be O of log n. Instead, it's going to be O of n because we need to check all nodes. How would you search through that tree looking for a node? Once again, you could do a traversal. That would work just fine. You'd have to then return true or false if you ever find it, but check out how else we can make this happen. We have here the search tree method. It's looking for this data value within the tree that's currently rooted at P. So we start by calling this method with the root. We look for the data value. If the root is null, if P is null, there's nothing to be found, so we return false. Now, if we find the data value at P, so if data equals P.data, return true. Else, we have not found it. What do? We look everywhere. We look on the left, we look on the right, and we OR those 2 results together. So imagine that the value we're looking for is found somewhere on the right subtree, somewhere way down. But of course, it's therefore not on the left subtree. So ultimately, this will return right here. It's going to return false or true, which will ultimately be true. I encourage you to use this exact tree that we had right here and trace through this code that you just saw, this code, using that exact tree and make sense of what's actually happening when we actually OR those 2 results together. One more, I say it's just an exercise. I would encourage you to pause the video and you try to solve this one on your own. Write a method that will print out all of the values in a binary tree that are greater than or equal to a particular value that was passed to this method. So here we have a method called print values larger than. We send over the root of the tree and we send over the value that we want to print all nodes that are greater than that value. How would you do this? Pause the video, think about it. I'll leave you with an answer, but I'm not going to code it for you. I'd like you to try coding this one yourself. Ultimately, we need to visit every single node. So it's really, once again, just a traversal. You pick your traversal, pre-order, in-order, post-order. If you post-order, you want to get excited, go to the breadth first traversal, but really just do a traversal. And instead of printing the node, we conditionally print the node. If the node is greater than the given value, print it. Otherwise, go left and then go right. Was it fabulous? I don't know. Our demotivator from despair.com. Dreams are like rainbows. Only idiots chase them. That's not nice. Have dreams, chase them. In positive moods these days. As always, if you have any questions, feel free, leave a comment, get back with you. Take care, everyone.